Okay, good morning, everyone. First of all, I would like to thank the organizers for the kind invitation. I'm very honored to speak at this workshop. So in this talk, I will report some progress on sampling discretization of LP norms and its related applications in sampling recovery. So let me start with a list of references for the results I'm going to present. My main focus, will be on my recent collaborations with Volodya, Chimnakov, Igor Kosov, and Sergey Jehalov. So of course, this.
Could you speak up a little bit?
Oh,
I don't think people
okay.
hear you.
Thank. Of course, the list here is far from being complete. There are many important results in this area, which I will not be able to report. But anyway, fortunately, we have this excellent survey paper. So if you are interested in, this area, so you can, I highly recommend this survey paper. So basically, you can find almost everything in this survey paper, or all the results, known results in this survey paper. Okay, to begin with, let me just introduce some notations for the rest of my talk. So I will fix this notation to denote a probability space. Here, mu is a probability measure on this set omega. And in general, mu is a very standard probability measure. It's normally unknown, maybe. Yeah, LP space is defined in the regular way. This is LP norm defined with respect to this measure mu. And normally, it's very hard to compute this LP norm because, this mu is a quite general measure. And here we assume p smaller than infinity. So in my talk, I will not discuss uniform discretization. So I will always assume p smaller than infinity. And we use this notation. This is, I think, a standard notation to denote the regular little LP norm in Rm. And if we put this m as a subscript here, we will use this notation to denote the normalized little LP norm. These are discretization norms that will be used in the formulating of our result. Okay, and we are mainly interested in discretization in high-dimensional spaces. So I will use Xn to denote an n-dimensional space of bounded functions on omega. Yeah. So this is our space. Oh, yeah. Oh. Okay, this Xn is n-dimensional space of functions, bounded functions defined on omega. Here we assume functions are defined everywhere on omega, so that pointwise sampling is possible. Okay. Now let's turn to our main problem. So here is the formulation of our problem. Our main problem is to discretize this LP norm. The LP norm is defined with respect to this probability measure, which is probably unknown. Discretize this LP norm through this discrete sum, which is the normalized little LP norm. And so our aim is to establish two-sided estimates with general constant C1 and C2. And here in this finite sum, so there are some points here. So this is, you have a finite set of points in omega. And basically, you have a function f from the space. You restrict the function. Initially, the function f is defined everywhere on this large set omega. Then you restrict it to this finite set. And then this is discretization. Then you take the normalized little LP norm. Right? After the restriction, f is more or less like, it can be seen as a finite m-dimensional vector. Okay, and of course, we want this discretization to be uniform for every f in the space. So the set of points should be independent of the function f, and the constants c1 and c2 should be independent of both f and also n, because we would like to consider the asymptotic behavior of the problem as n goes to infinity. So a problem like this is called a Mason-Quist discretization problem. It's called, this is a standard natural extension of the classical Mason-Quist inequality for trigonometric polynomials, right? And this inequality, inequality of this form is called Mason-Quist inequality with constants C1 and C2. We are particularly interested in the case when C1 and C2, both of them are very close to 1. In this case, you can actually write this inequality in this form, right? They are equivalent. Yeah. So, but this is, and also, for this problem, so when we calculate the discrete sum, also there's a weight here. All the weights, this is the uniform weight. They are equal here. Okay. For this problem, there are actually two important parameters here. First one is n, capital N. So this denotes the dimension of the space. The second one is little m. Little m is the number of points required for this discretization. So this is the number of terms in the sum, or the number of points required in this discretization. So remember that we will keep these two notations throughout the talk. So capital N denotes the dimension of the space. Little m denotes this number of points required in the discretization. We will mainly consider the asymptotic behavior of this little m when the dimension n goes to infinity. So this is our main goal is we try to estimate this little m in terms of the dimension capital N. That's a very trivial lower estimate of this little m, because this inequality clearly implies little m is bigger than or equal to the dimension n. So we will try to, under certain conditions, so our aim is to get some matching up point, probably with additional log factor. Okay, in this framework, so the space Xn can be either real space or complex space, but for simplicity, I will always assume space is real. Okay, let me just give a few comments on this problem. Yeah, this I learned from this excellent survey by Johnson and Professor Shaxman. So actually, there are some very deep results on invariance of finite dimensional subspaces of LP omega into this little LPn that are closely related to sampling discretization of LP norms. In fact, there are some techniques developed for those invariance theory problems are extremely powerful, have proven to be very useful for sampling discretization. We use a lot of techniques in this area. So, and I also, this is an excellent survey on this topic. Yeah, you can find, many interesting results, and also the techniques are summarized very nicely in this survey paper. Okay. And the second comment is, the Mason-Quist discretization problem has close connections with several other areas. So here we formulate the Mason-Quist discretization problem in terms of this Mason-Quist inequality I just mentioned, because hopefully, people in approximation theory can, it's easy for them to understand this problem. But actually, you can formulate this problem equivalently, in different settings. For example, you can formulate Mason-Quist inequality, this discretization problem equivalently, in terms of P frames or spatial properties of operator norms of submatrices, and also moment estimates of, high dimensional random vectors. You can see all those collections in this survey paper. But I will mention a little bit on this moment estimates of random vectors, because we will also consider a probabilistic approach to this Mason-Quist discretization. So the problem, the question actually is the following. So instead of some particular points, So we choose the points randomly, and so those are RID random points selected from the distribution mu. And so then we consider this is essentially the Mason-Quist inequality. So this is the LP norm, raised to the power p, right? This is the Mason-Quist inequality with epsilon. Okay, and because these are random points, so this inequality defines as even. We want to have this inequality with large probability. In other words, we want to find an estimate on the number of independent random points, so that this inequality holds with large probability. So this, you can formulate the Mason-Quist problem in this probability setting. Okay. Because we are working in finite dimensional space, we can also reformulate this problem very easily. Say, for example, you just start with any basis of xn, you put all the bases together. So then you have this finite dimensional vector, right? And this is a vector valued function defined everywhere on omega. But if you evaluate them at those random points, you have random vector, right? Say, first of all, you evaluate this vector at this vector at this point, and then these are independent copies of this random vector, right? And then let's see what is function f. Because now with the basis given, you can identify the function f with a vector in Rn in this way, because this is the basis. So every function in X and can be written like this. So then this expectation can be written like this. If you identify f with y here, the vector here. So this is dot product. And similarly, for this finite sum can be written like this. And so the supermom, the set of this, over which the supermom is taken, can be written like this. This is a convex body in Rn. So basically, this inequality can be written like this. So, so this is so here. So when you look at this inequality 4, so here. Actually, you can formulate it in a very general setting in probability. You start with a high-dimensional random vector, right? Then consider UJs are independent copies of this random vector. Essentially, you discretize this expectation through this finite sum, right? And this here is a linear function. Okay, and so then for this Mason-Quist problem, we want to know the conditions, estimates on M, so that this inequality holds with large probability. But in this setting, you can simply say the following. So how many independent copies? So M is the number of independent copies, right, are needed of this random vector are needed, so that this inequality holds with high probability. So this, is the same formulation. Yeah, just one example. Mason-Quist discretization problem can also be formulated equivalently in several other ways. Okay. Now let me mention several results in this area. So we start with the space of L2 space. So in this case, this is the only case we can get a very ideal result. So here, so we because we want to this discretization with equal weights, so we have to make this assumption on the space. So this inequality in approximation theory is called a Likovsky inequality because it compares the L infinity norm with the L2 norm, for functions in Xn. By the way, this L infinity norm essentially is maximum. I don't consider, because I assume functions are defined everywhere. So I should use a maximum over the domain omega. Okay, so under this Likovsky assumption of Likovsky inequality, which compares L infinity norm and L2 norm, so then we have this inequality. This is a Mason-Quist inequality, of course, with some constants. And so our main interest is this little m. Little m is the number of points required in this discretization, right? So clearly, in order that this inequality is true, m should be at least equal to n, right? So m should be bigger than or equal to n. But remarkably here, in this result, we also have a matching upper estimate. Forget about this general constant. See, I just consider asymptotic order. Suppose n goes to infinity, so the order of m is more or less like n. This capital N is exactly the dimension of the space. So that's low log, additional log factor here. If you put additional log factor here, this result was learned many years ago. And so you have this, this is almost a sharp estimate, right? If you forget about this general constant, then you get this. So this is for L2 case. Let me just give a few comments on this result. So first of all, this result was first established by Limonova and Chimnyakov in 2020 with general constants, 1 minus epsilon, 1 plus epsilon are replaced by C1 and C2 general constants. And then the result was improved by Igor Kozov. So their proof actually depends on contains two ingredients. First one is the proof used this very famous paper theorem. So I won't formula is on Frame. So yeah, this one and this is the main ingredient in the proof of this theorem. So the second one is a certain iteration technique. Okay, so this is for L2 case.
May I ask a question? Yeah, just about this constant k. So because this refinement by Kosov, yeah. So when if you put k, multiply k, which is bigger than 1 with 1 plus epsilon, yeah. So then the upper estimate. Is probably that's with epsilon, yeah. So what is the point of having it?
That's a very good point. Actually, because you can use that's a change of density argument. So you can, after if you consider here, I consider equal weights, right? If you put a general positive weights here, use the change of density argument. So you can put k equals 1. So here you can choose k equals 1. So that will follow from this general result.
Okay.
But in general, it's unclear whether k can be equal to 1, whether this k can be dropped or not. But certainly, from the proof, this is needed, right? So, okay. So now let's consider LP case when p smaller than 2. So in this case, we can get a slightly weaker result under the same assumption. This is Likovsky inequality for L infinity norm and L2 norm. And why we consider this inequality? Because in applications, this inequality is relatively easier to verify. Yeah, it's collected, say, in approximation theory, we know it's collected in terms of crystal functions. In many cases, so this Likovsky inequality of this type for p equals infinity, q equals 2 can be relatively easier to prove. Okay, this is the same assumption as in theorem 1, right, for L2 discretization. And this same assumption, but here we assume p strictly smaller than 2. And we have this discretization result. But here we don't have k, but the price is we have additional log factor here. Yeah, k times n log n. Yeah, and also but you also have some additional log n when p is strictly smaller than 2. Okay, so so this is a discretization of LP norm for p strictly smaller than 2. But still, it's very challenging problem to say whether this log n, this additional log n factor can be dropped. This is very hard. So, so this is for LP discretization for p smaller than 2. So you may ask why we needed to assume p smaller than 2. Actually, we know that when p bigger than 2, the result is not true. So under this same assumption, on the Likovsky inequality, the Masson-Lewis inequality will require at least say n to the power p over 2. Since p bigger than 2, so p over 2 is bigger than 1. So it will require significantly more points as n goes to infinity, right? For the Martin-Quiz discretization of LP norm for p bigger than 2. For the general space, and this cannot be, this is a lower estimate, so you cannot, you have to get at least n to the power p over 2. These points in order to get the discretization for LP points. However, so if you change it, replace this condition by a slightly stronger assumption, because p bigger than 2, you have this one. And this inequality is actually stronger than this one, for p bigger than 2. And a similar result, you can get n times log n to certain power can be obtained. This was done by Kosoff in 2021. But that's some, in literature, in many cases or applications, we would like to have this Likowski inequality instead of this one, because this one is very hard to verify. Say, for example, if you choose the space, to be some maculary trigonometric polynomials, then for p bigger than 2, this is difficult. It's unclear whether this is true. But p equals to 2, this is always true. Yeah. Okay. So these are the. So now let's turn to the random approach to the Martin-Quiz discretization problem. And here we, So here our question. So again, we want this Martin-Quiz discretization, this Martin-Quiz inequality. Okay, but the difference here is instead of particular points, we choose cosj to be random points. They are independent RID random points selected from the distribution mu. So we wanted to have this inequality with large probability. So this is the first thing. So difference, the set of points are chosen randomly. And the second difference is, so this W, this class, is a more general class of functions. In the above two theorems, we always assume W is a linear space. And here, one typical example, we can choose W to be finite union of, say, n-dimensional subspaces. But the problem is the number of these n-dimensional spaces in the union can be very big. Right? So, and the W is no longer to be assumed to be a linear space. So a general, maybe compact set. So we want to have this discretization with high probability. Okay, the general approach to this problem is based on covering numbers. Yeah, this is defined. We use epsilon entropy. So given epsilon bigger than 0, so this epsilon entropy of a compact set in a Balmer space is defined in this way. And what is this? This is the covering number. This is the smallest number of balls of radius epsilon required to cover the set A entirely. So, and we have this, it's just a definition. And using this concept, we can formulate the general result like this. Okay. So, first of all, let me put some conditions on this class of functions. So just keep in mind, in applications, we just choose W to be a finite union of some relatively lower dimensional subspaces. Okay, but the union of those subspaces, the number of those subspaces in the union is very big. So first condition is this one. Clearly, if W is union of linear spaces, this is satisfied. The second one is Likowski inequality for LP. It compares, this is L infinity norm, this is LP norm. So this is Likowski, just these two conditions. And then after that, we start with random points selected, RID random points selected according to this distribution mu. And then, so we have this inequality. This is Martin-Quiz discretization inequality. And this is uniformly for functions in this class. Yeah. So normally, in the beginning, when we formulate this is an n-dimensional space. Now we consider a general class of functions. So, and this hold with high probability if, so we wanted to find estimates on M, conditions on M. So what is M? So m has this estimate for any integer m satisfies this condition, then we have this inequality with relatively high probability. So this is the result. Yeah. Okay. And so this. So in order to apply this result, we need to estimate the entropy numbers in an infinity norm. But there are many tricks in functional analysis to do this. Okay. So our main application of this theorem is in the universal discretization. And here we choose W to be a union of finitely many V-dimensional subspaces. V is relatively small. So let me just formulate our general setting. Okay. And so we start with a system of functions, bounded functions on omega, the general system of functions. And here, so we don't need to assume they are also normal. But mainly, let's start with a system of bounded functions. And so of n functions, n is number of functions. And we also have another integer v. And v will, in this setting, denotes the sparsity. Normally, v is much smaller than this capital N. Okay, and then we consider, given this system, we use this notation to denote the set of all v sparse functions. What does it mean? It means every function in this class can be represented in this form as the number of terms in the sum equals v. But the problem is, this is a nonlinear representation because the set J depends on f. Right? You can, if you consider all functions in this space, then J will range over all subset of this set with cardinality equal to v. So the number of those subsets is very big. Right? But v is relatively small, but n is very big. So here we have two parameters. So n is the number of functions in the system. This little v here, this is the sparsity. But v is our main parameter. So we will try to estimate the number of points in terms of this sparsity. Okay, and then we can formulate our universal discretization. So this is a formulation. So and so this is a Marcinkus discretization inequality with equal weights. So, and we would like to have this inequality for every v sparse functions. Yeah. So instead of giving n-dimensional space, now we consider this sigma v essentially. This is a finite union of all v dimensional subspaces of space generated by the system. Okay. So this is our inequality. We wanted to have this inequality uniformly for all f, for all v sparse function, and the number of points required in this discretization. This is m. So this is our problem. This is called universal discretization of LP norm for sigma v dn. I think the universal discretization, this concept first appeared in early paper of Lodier. So here we apply just a slightly changing the definition. Okay, and if we consider p equals to 2, so this is actually not new. If we consider p equals to 2, if the system is an orthonormal basis, and then this is just the RIP property can be formulated as RIP property of the matrix. You can think it in this way. You start, suppose this is an orthonormal basis, and then this is a vector valued function, right? And then you just restrict this vector valued function on a set of on this finite set of points. Then you can represent this function as a matrix, right? But the sparse, this universal discretization can be written equivalently in this form. It's very easily seen. So this this is exactly the definition of RIP property of order V, because we want this equality not for every Z in Rn, but for every V sparse vector in Rn. So this is RIP property for P. But here we need to assume is also normal basis. In our general formulation of this universal discretization, we don't need this condition. Okay. Now let's turn to our result on universal discretization. This is a direct application of the general theorem 4. So, and here we assume we have this system of functions. So we put some conditions on system. The first condition, actually this condition is a little bit, it's too bad. It's uniformly bounded one. We know that there are a lot of orthonormal systems that doesn't satisfy this condition, but all the method highly relies on this condition. So the second one is this inequality. So actually, this inequality, if you forget about the constant k, this is true for any linearly independent system. If the system is linearly independent, you can always find a constant k. But of course, the k can be very big. So, but this is our assumption. So we want to have a quantitative estimate. So we specify this constant k. So we make this assumption. So these are two assumptions on our general system. Okay, and so after that, we start with RID random points. And we have this discretization, universal discretization for every V-sparse function. And this universal discretization holds with high probability if M satisfies, for any M satisfies this condition. But if you look at this estimate, forget about the log factors. But the main term is V. V is a sparsity. We know that even if you have one space, one V-dimensional space, so M should be at least V. So this, up to a log constant, so this K times V, this V is almost sharp on the order here. Okay. So again, so this result holds for p smaller than or equal to 2. So this is our the result on universal discretization. And okay, so let me give one application of this result. So in optimal recovery, sampling recovery. So let me just introduce some notations. Okay, so assume that we have a finite set of points. And also, we assume that we have this universal, we just consider p equals to 2 here. So consider we have this universal discretization for two V-sparse functions. Suppose we have, this is known. And then for each function f, so we have this finite set of points. We can restrict the function f on this finite set. This is discretization. So the restriction can be considered as a vector. So this is a sampling operator. Basically, this is a restriction of f on this finite set. Okay. And because of this inequality, we know that if f is V-sparse, here this inequality is 2V. So if f is V-sparse, then this f is uniquely determined by the sampling. So, and for every V-sparse function is uniquely determined by the sampling operator. Okay, then the question is, so can we build a sampling algorithm, so defined on the, so that f can be recovered? Every V-sparse function can be recovered through this algorithm, right? So this is a very natural question. And there are some algorithms in literature which answer this question. Say, for example, for this RIP property, let's return here. If we make the additional assumption that the system is orthonormal basis, and the universal discretization simply means this matrix has the RIP property of order 2V, right? And if in addition, C1, these two constants are very close to 1. But this is very important in the proof of this RIP property in complex sensing. So those C1, C2 are these RIP constants are very close to 1, roughly speaking. Then we know that every V-sparse function can be recovered through this sampling, through this L1 minimization. And you can also formulate the equivalent in terms of some optimization like unconditional optimization like Maslow method. So basically, this is a algorithm. This is L1 minimization. So this is known. But in this result, there are two crucial conditions. First of all, the system has to be orthonormal. And secondly, the constant C1 and C2 are very close to 1. Actually, that's also one implicit assumption. So this kind of discussion has to be in L2 space, right? So now instead of this, this well-known L1 minimization in complex sensing, we consider this weak Chebyshev greedy algorithm. We use WCGA to V-sparse function, and we try to consider this weak Chebyshev greedy algorithm. I will give the definition in the end of the lecture, but here I will just assume this is algorithm. So let me just give a few comments on this algorithm. So if we compare this WCGA with L1 minimization, so this algorithm is applicable to p bigger than or equal to 2 as well, and also does not require assumptions that the system is orthonormal basis, and also the constants are close to 1. This is the advantage of this algorithm. Okay, and of course, crucial importance in our discussion is certain Vega type inequality for WCGA in Q-smooth spaces that was previously established by Volodia and his collaborators, but these are very deep results. Yeah, we will just use those results. Okay. Just for simplicity, I will consider only formulate the result for p equals to 2. And so in this case, WCGA is just the weak orthogonal matching pursuit. Yeah, I will give the definition later, but here I just, so this, when we apply this weak orthogonal matching pursuit, that's a weakless parameter T, and also a dictionary. And this weak orthogonal matching pursuit is applied in a Hilbert space. So I will use this notation to mean this algorithm applied with a weakless parameter. And okay, sure. Yeah, I will finish. Okay, so okay, so let's explain the idea. So the main assumption on the system here, we make this stronger assumption, but this one can be weakened a little bit. So this is basically is a real system, and also the universal discretization. Yeah, we have this for general constants. Here we do not assume those constants are close to 1. And the main idea is, so instead of functions f on the whole domain, we first restrict everything on this finite set. So then we have a vector, right? We restrict each function on this finite set. Then we can apply our algorithm to this finite m-dimensional vector. To this, we can also restrict the system on this finite set. So we can apply this algorithm in Rm, m-dimensional space, which is very easy to implement. And then, so after that, we use universal discretization to return to the space L2. Let me just to be a little bit more precise. So for every function f, this is a sampling operator. I will just for simplicity, I use this notation. This is an m-dimensional vector. So and also we can restrict every function in the system on this finite setup. So we have a new system. This is a system of in Rm of vectors in Rm. So after that, we apply, giving a sparsity, this parameter v, we apply this algorithm, but choose this vector, and but then we use, this is the iterations. We use this notation to denote the approximation to this f hat of 10 at this iteration of this algorithm. This is essentially a greedy type algorithm, can be written like this and term. Okay, after that, we can return to this operator, the initial definition on the initial domain omega. So, and finally, so we can formulate our main result. So this is, we already mentioned this algorithm. We have this, the bigger type estimate. Basically, this is the best M-term approximation in L infinity norm. In particular, if F is V-sparse, and you can choose G to be equal to F. So this is 0. So this means every V-sparse function can be recovered exactly through this algorithm. Okay, and finally, but this one I think this is very, very well known, so I don't need to give too much expectation. So, but the only difference here is you have a weak this parameter, right? But it's very easy to understand its iteration. Okay, so let me just stop here. So thank you very much.
Thank you for your interesting talk. Are there any questions?
Does the dimension of omega plays a role, or could it be in the set?
Yeah, omega here, yeah, we don't have consider. This is a general set. So
Okay.
we even do not need to assume this omega is a subset of Euclidean space, yeah.
So your random point psi could be trajectories, for instance?
Yeah, independent of the underlying dimension of the domain. Yeah, yeah, thank you. Yeah.
It's not a question, it's a comment on the remark you've made about L1 minimization.
Yeah.
To have exact recovery, you would need C1 and C2 to be close to
Yeah.
1. There are arguments that you can do it without this condition. So
Okay.
C1 and C2 can be.
Okay, thank you.
It will. What will happen is that in the number of m, instead of scaling with n, so you will have the ratio of C1 over C2, C2 over C1, C2 being over C1.
So in the initial paper, I think as
Yes,
we
in
have
most
this.
papers
this
with this, but there are
there are some
somewhere.
Okay.
I forget it well, but it can be done with this.
Okay.
Different from one.
Okay. Thank you very much.
This one I will show you maybe.
So in general, constant C1 and C2, this is applicable. Okay, thank you.
At some point there was some integral of entropy.
Oh,
It's not so important for people. This is similar to things that Dudley did.
Oh, yeah. Actually,
my question is, there are stronger things of Talagan, chaining method and things like that. Do you use something like that?
No, actually, we didn't use Danny's entropy as for this one. We used something slightly different. We still do not know whether this estimate can be this one. Yeah. Sorry, just. Oh, sorry. Yeah.
That's right.
Yeah, we still do not know how to use this Danny's form to get this one, this general. And also, yeah, I understand your question.
You know about this chaining.
Yeah. It's very. We just do not know. We know that this estimate normally will give additional log effect. Yeah, thank you.
Just wanted to make sure that we know.
Yeah.
Mario?
Can you show the slide again to further with the sparse discretization, please?
This,
One more, please, with the result for LP for P between 1 and 2. This one, exactly. So.
Oh, yeah. This one, right?
So there the M scales with V, right? Just with
yes, yeah.
Do you have a lower bound for that?
No, we do have actually in all my paper with Volodia. We actually show, of course, M is clearly the least one should be bigger than or equal to V, right? And then in our paper with Volodia, we showed that log n in general is needed.
Because there is just as a comment, there is something for sparsification of binary matrices, where you know that you only need V to the power P for P smaller than 2. There is a famous result that P equals 2 is the singularity. But just I can show you later.
Okay, thank you. Yeah.
Okay.
Yeah, but on the same slide, how the constant depends on epsilon?
Oh, yeah.
Something better, right?
Yeah, this is also related to Professor Shaxman's question. So our method doesn't give better dependence on epsilon. Yeah, the dependence is very worse. So if we can get if we want to have better estimate, probably we need to improve our general result. Yeah. Yeah, this is probably epsilon to the power -7, something like this. It's too bad here.
Yeah, thank you.
Yeah, thank you.
Okay, thank you very much for your lecture.